First, let's review our perfect squares. Most of you know these. 1 squared is 1. 2 squared is 4. 9. Take a moment, fill in the rest of those at least through 10. Eleven is 121. 12 is 144. If you can memorize 13 squared is 169. Then you automatically have 14 squared memorized because you take the 6 and the 9 and you switch them. 14 squared is 196. 15 squared is 225. There are 2 numbers that we need to add onto this chart. 16 and 25. 16 squared is 256. 25 squared is 625. Okay, remember the difference of 2 squares. If I have something like x squared minus 256, that would factor into the square root of x squared is x. The square root of 256 is 16. It would factor into x plus 16, x minus 16. So take the square roots, 2 sets of parentheses, 1 with addition, 1 with subtraction. We're going to do that exact same thing, but with slightly larger exponents. This is called quadratic form when the exponents are larger than x squared. 16 is on this chart. It's the perfect square of 4. 81 is the perfect square of 9. What can you multiply times itself to get x to the 4th? X to the 2nd. X squared times x squared is x to the 4th. So the square root of x to the 4th is x squared. You basically take that exponent in half. So this would factor into 4x squared plus 9, 4x squared minus 9. Do you think we're done?
No. Well, wait, yeah.
X squared plus, that one's done. What about this one?
No.
Not done. X squared minus, you're likely not done. 4x squared is the perfect square of 2x. 9 is the perfect square of 3. So that one will split into 2x plus 3, 2x minus 3. And we still have that 4x squared plus 9 in front. This is why we had to add 16 squared and 25 squared. They're going to really enjoy using the perfect squares of perfect squares so that when you take the square root the first time, you still have a perfect square and you can take the square root again and do more steps. So they are going to really, really favor the number 16, 81, because the square root of 81 is still a perfect square, and 256, 625. You're going to see those numbers used quite commonly because they are perfect squares of perfect squares. All right, let's try B. 625, what is that the perfect square of? 25. What is 256 the perfect square of? 16. Now this x to the 8th, what's half of 8? 4. X to the 4th times x to the 4th is x to the 8th. Basically take that exponent in half and that will give you the square root. So this is going to factor into 25x to the 4th plus 16, 25x to the 4th minus 16. The first part's done. X to the fourth plus, that's fine. What about x to the fourth minus? We can probably keep going. 25 is the perfect square of 5. X to the fourth is the perfect square of x squared. 16 is the perfect square of 4. So this one goes to 5x squared plus 4, 5x squared minus 4. How many of you are seeing x squared minus and thinking, oh my gosh, are you kidding me? We're not done yet. But good news, is 5 a perfect square? No, if you try to take the square root of 5, you get a crazy decimal. So in this case, you see x squared minus and you think, oh my gosh, I might not be done. 4 is a perfect square, but 5 is not, so you are done. What's wrong with C? Everything. There's a negative at the beginning. So our first step is going to be to factor out a negative. I think you actually, no, you can't. Never mind. So -1, that would give us 16n to the fourth minus 625. All this means is you're going to have the same thing that we did in A or B. There's just going to be a -1 in front of the final factored form. So on your own, I would like you to pause the video. Try factoring 16n to the fourth minus 625 on your own. On the next page, we're going to look at trinomials that have larger exponents than what we're used to factoring. The first thing that we need to do is check greatest common factor. It'd be really nice if we could divide all of these by 3. Can we divide all of them by 3? Yes. And then all of them have x's. How many x's can we pull out of all of them? 2. So we have 3x squared. And some of you need to see this visual. So if you need to write divided by 3x squared underneath each one. So 3x squared. We'd be left with, what is x to the 6th divided by x squared? X to the 4th. 15 divided by 3 is 5, and we'd still have x squared. 18 divided by 3 is 6, and we're taking the x squared out. Okay, now some of your problems on your assignment are going to start like this, where you factor out the greatest common factor. Some of them are going to start just with this part that I'm highlighting. So if there isn't an x on that last term, you're not going to be able to factor out a greatest common factor. If there is an x in that last term, definitely factor out a greatest common factor first. Okay, now this might look a little bit weird, but I have a trinomial, so I'm going to look for two numbers that multiply to give me 6 and add up to 5. 2 and 3. So using what we know from previously, that would factor into x plus 2 times x plus 3. But can this be right? No. If I multiplied this out, x times x would give me x squared. I really need it to give us x to the 4th. Could we tweak this? Make it squared. Make it x squared plus 2, x squared plus 3. Then when you multiply it, x squared times x squared will give you that x to the 4th. X squared times 3 will give you 3x squared, 2x squared. Those will add up to that 5x squared. And then the 2 times the 3 will give you the 6 at the end. So by taking that x and turning it into x squared, it fits this. We complete our answer by putting our 3x squared out front. And here's a helpful hint for all of these. Do you see how we start with x to the 4th and then the middle one is half that. And this x squared is what we end up using in our factored form. Okay, just think about that as we move to problem E. First of all, greatest common factor, and this one's kind of funky looking.
2.
2, anything else?
Yeah, x3.
X to the 5th.
Oh yeah, I get it.
So x to the 13th divided by x to the 5th. You've got 13 on top, 5 on the bottom, so you're taking 5 away from the 13. That leaves us with 8. Still a very large exponent. 10x to the 9th divided by 2x to the 5th would give us 5x to the 4th. And 8x to the 5th divided by 2x to the 5th gives us 4. All right, we are looking for two numbers that multiply to give us 4 and add up to 5. 1 and 4. Now we just need to think about what type of x we need to put in these parentheses. Because we started with x to the 8th, and this middle number is x to the 4th, we do x to the 4th plus 1, x to the 4th plus 4. Aren't you glad those are pluses and not minuses? Because if they were minuses, what would we end up doing?
Yeah.
When we do more, it'd be so much fun. Because we love factoring, right? Yeah. Okay, I would like you to try F on your own. Keep in mind, see how that 2 after the W doesn't look like an exponent? It's supposed to be an exponent. That's definitely a W squared. So give F a try if you're watching the video. Pause the video, try it on your own, and then play again. How many of you are looking at the subtraction and thinking, oh crap, we're not done? But 2 and 3 are not perfect squares, and quite frankly, W to the 3rd is not a perfect square. So this is good. We should actually look for sum and difference of 2 cubes when we see W cubed, but 2 and 3 are not perfect cubes either, so thankfully we are done with that one.